Okay, it stops at 2929. It's an interesting thing because if this can be sold as a camera and not a video camera, if it stops automatically recording at 2929. So if you have if you're buying a video camera that will be able to record more than 2929, it's because of the cost. So if you have a video camera that can go beyond that, it will be more costly, or some tax purpose or something like that.
Sounds like something maybe from 1980.
But the rule still, I was like, this is not that old. But yeah, anyway, 2929 anyway. So no, 2959, sorry. So we got chalcophile, we have a bunch of chalcophile, siderophile, and these all are related to industry applications too. Okay. All right. Now, organophile is like anything that associates with organic molecules: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, sponge elements. It's easier. Sponge. The organophile. They're coming up with names now. Anyway. There could be some metals too: uranium, vanadium, germanium, lead, molybdenum for this. Just let's focus on the important ones. Because the Earth, it's geochemistry after all, Earth is made up of the crust, mantle, which are basically the siderophiles, and the lithophiles, and the core, which is the siderophile. Atmosphere, atmophile, and the water. So, I don't know, hydrophile or something like that. Okay. So this is important when we are talking about, this is like the geochemical classification. Let's think about something which is called the cosmochemical classification of elements. So there was a person in Washington University where I did my PhD from. Her name was Katharina Lotters, and she with a co-author, with one more co-author, Bruce Fegley. So Katharina Lotters and Bruce Fegley did the research that I'm going to present here. So they came up, this idea existed, but they kind of formalized this idea of classification of elements based on how quickly they so imagine you're forming, so there is a planetary nebula, like gases and everything, or the solar nebula. Our solar system is just forming. Just imagine that, it's all gases and everything. What do you think that composition was when our solar system was forming?
Primarily hydrogen.
And why do you think that's correct?
Because that's what, if you look at Jupiter and the sun, that's primarily what it
Sun takes. So if you can somehow measure the composition of the sun, you will have a general idea about the composition of the solar system. Because rest of the things are so small by weight, they don't even count. Like our Earth does not matter. Even maybe Jupiter, but even then, so the sun is basically, so sun's composition is from where we start. So how do you get sun's composition? It's easy to say start with the sun, but how do you know what's the composition of sun? And it's not just, it's the major part is hydrogen, helium, but...
Was it spectra that did it for us?
So there are two ways. So you can actually place a camera towards the sun and visualize and take the information from that. But a normal camera only sees in the visible to near infrared. So we only see in that visible range. Okay. If you may have a camera that can also see in infrared, near infrared, thermal, so the entire spectrum. So if you can somehow, so maybe one camera won't be able to do it. You need different cameras. So you basically use spectroscopy To find out, we'll go into that in not in this course, in the next course, the planetary geochemistry, if you guys take. You can do it by spectroscopy. The other thing is meteorites. It is a very, and there's not all meteorites. There are certain meteorites which have very similar solar composition. It's amazing, like this thing. So imagine you have all these gas clouds in the solar system. It's not a solar system yet. It's going to form a solar system. So you have that. And then things start to form. So things start to collide. And once you have a small molecule that attracts more molecules through gravity, and you start forming these things. Now, if you can there are certain things in our solar system available. They're called calcium aluminum inclusions and things like that. I'm not trying to get too technical in here because it's all about cosmochemical classification, but I'm just giving you a teaser that there are things like calcium aluminum inclusions in meteorites that has the composition of the solar system of when it started, kind of like that. It's the composition of that solar nebula was kind of captured in these things, which is very similar to sun, and it's astounding, the similarity. So we kind of assume that the composition of the sun is from these two sources is kind of we kind of understand the basic composition. So we have the composition. Now, the pressure at that time, let's assume it was really less, okay? But the temperatures were really high, okay? So let's assume they were 2000 Kelvin or something like that. And then solar system begins to cool down. Now, when it begins to cool down, things start to form metals, because when you heat something, it's in the gaseous state, and then when you cool it down, it goes to liquid and then to gas. But a process was similar to sublimation when gases directly convert to solids. It's called condensation. That part of condensation, when you have vapor and you're going to the solids directly without going to, so this is called condensation. The opposite is called sublimation. Condensation is just you're making a denser phase. So vapor to liquid is also called condensation. So you're densing it up, basically. So when you're going from vapor to solids, you're doing this condensation thing, and you're lowering the temperature. That is, the lowering the temperature is leading to condensation. So the things that are more refractory will try. So if I start raising the temperature of this room, the things that will first vaporize are things like if you have organic solvents, like alcohol or acetone or things like that, because they're really volatile. So they don't need a lot of heat to vaporize. So the things that easily vaporize are called volatiles. So you have volatiles. And things that do not vaporize easily are called refractory. Okay, so I'm just trying to draw this. It's called refractory. So all these organic things could be here, H2O, methane, organic things. Things will be like rocks, and these things could be here. So liquids, organic things could be here, rocks could be here, okay? So this is the temperature. So your temperature is increasing this way. So this process is going from, this is the sublimation process, temperature is increasing. But when the solar nebula was formed, the temperature was actually coming down. It was cooling off. Right? So if you just think about the reverse of this process, when things were cooling off, what was the first thing that will cool off? The most refractory or the least refractory? The most, right? So the things, when started to cool off, the most refractory things started to cool off first. And Lauders, so Katharina Lauders and Bruce Fegley, I think in their 1998 paper, they did this. Both are at WashU. I've taken class from this guy. So I studied thermodynamics from this guy. So the book and everything is like, it's fascinating. Katharina doesn't teach, she's just focused on research. So this paper is like cited like tens of thousands of times. It's like amazing work. So they actually calculated, so they started off with the sun's composition, and mathematically they calculated the condensation sequence. And then based on whatever things started to condense out first, they were the most refractory, and then less refractory than them, then a little bit more refractory, then volatile things. I'll just write that order down, okay? So highly refractory. So highly, okay, 5 minutes. Highly refractory, rhenium, osmium, zirconium, hafnium. They will only vaporize at temperatures above than 1700 Kelvin. Okay, then comes highly refractory, then comes refractory, 1500 to anything that condensed out between 1500 to 1700 Kelvin, aluminium, scandium, calcium, titanium, most rare earths, thorium, uranium. Moderately refractory, 1300 to 1500 Kelvin. Beryllium, magnesium, silicon, chromium, iron, cobalt, nickel, niobium, cerium, ytterbium, platinum, palladium. Then comes moderately volatile, (1100 to 1500). So now you're getting into the volatile. I don't want you to remember these. I'm just writing it because so that if you have somewhere this thing written down. Copper, barium, manganese, strontium, phosphorus. What is Au? Yep, gold. Moderately volatile, 700 to 1100 Kelvin. Sodium, potassium, boron, sulfur, rubidium, cesium, gallium, tin, selenium, highly volatile. Less than 700 Kelvin. Lead, zinc, thallium, this is Tl, indium, bismuth, oxygen, carbon, nitrogen, hydrogen, and noble gases. Okay? So I just want you to realize like how the different things are classified. So we have like a cosmochemical way, and this will be used to understanding like the different, so there will be refractory lithophiles and things like that, or refractory siderophile elements. These are the different crosses that we'll have when we are trying to study like the different planetary bodies. We'll continue this. Thank you. Okay, did you get the assignment? Oh, can you, is there a sheet left? Okay, thank you.
Sorry,
No worries, yeah. Oh yeah, no worries. Sorry, yeah, thank you.